RENET. RENET is an adaptive routing algorithm introduced by Hamdan and Arslan that reroutes flows based on bandwidth fluctuations in the network. The main idea is to recalculate optimal routes for flows as the network state changes. The flows are diverted to alternate paths to increase network utilization and quality of service. The main innovation over previous algorithms is that first, RENET handles physical fluctuations in bandwidth, not just congestion changes. And two, RENET uses a heuristic routing algorithm, which is faster than existing baselines. The algorithm starts with the k shortest paths as potential alternate routes. RENET evaluates each path by estimating the achievable throughput for its links, considering both available bandwidth and fair sharing among active flows. It selects a path that meets the flow's bandwidth requirements, or, if there are no requirements, the path with the highest estimated throughput.
Okay, so let's take a look at our code and see our implementation of the RENET algorithm from the pseudocode. So here we can see our path selection function, which takes in the source and the destination. And then we have our k parameter, which is the shortest path, number of shortest paths to consider. And then we take those k paths from the list of the shortest paths, which are taken from our graph data structure representing the topology. And this is updated every time links are added. Then we go through the first for loop, which iterates through the paths and attempts to find the expected throughput for each one and sort them. So we get the link from our link store, and this is also updated when links are added. And then we get the capacity, which is the current bandwidth, and the usage, which is the sum of the throughputs of all the flows on the link. And we do a simple subtraction to get the available bandwidth. And we also calculate the fair share, which would be the expected throughput if all of the flows are split equally. The throughput is split equally for all the flows. And we take the max of those because we want to be conservative with our estimate of the expected throughput. We want to err on the side of assuming it to be larger. And this is because we're going to be sorting them from minimum to max. And after sorting, we go through the second for loop, which is going to find the minimum expected throughput for the paths such that the expected throughput is at least the desired rate. And the reason for this is that we don't need to go better than the desired rate because all we want is the bandwidth satisfaction rate to be at least 100%. And if we can't do this, then if none of them are greater than the desired rate, then we just output the path with the greatest expected throughput. And so our return is the path.
The original experiment ran on a small real-world network with bandwidth fluctuation and on a large virtual topology without fluctuation. We use a medium-sized virtual topology to test the algorithm's scaling on larger networks with bandwidth fluctuation. We don't precisely replicate the original virtual network because handling bandwidth fluctuations takes more time and more computational resources on larger networks.
So let's take a look at the Mininet script for the setup. At the top, we have the hard-coded parameters, which is the starting bandwidth, which is 16 megabytes per second. The link change interval is the time between bandwidth fluctuations when we do the experiments with the fluctuations. And the ping interval is kind of representing our constant traffic generation pattern, which is just the time between pings on random host-to-host links. And then we have the 6 switches and 10 hosts. So here we can see the function which adds all the hosts and the switches and the links. And then down here is where how we do bandwidth fluctuations. So we replace links with a new bandwidth to represent a fluctuation. And here in simulate real links, we can see the new bandwidth is a random integer between min and max value that's hard-coded in. And then the rest is just starting the flows, running the experiment, doing ping tests, etc. Okay, so now let's take a look at the controller. At the top, we can see all of our REU imports. So we decided to do REU instead of ONOS because it's in Python instead of Java. And there's also a lot of built-in functionality that we could leverage since we're doing it mostly from scratch. We also have the desired rate is hard-coded, as we stated before, because the paper didn't tell us exactly how desired rate should be calculated. Then we have our initialization of the RENET controller, which generates a graph to represent the topology, and this is updated with an event handler every time a link is added. So here we can see the event handlers where we update the topology, and if we can see the usage and desired rate and stuff is set in there, and then the update topology function uses that graph data structure to add nodes and edges for the links. And we're also able to output this graph as a visual, so we can see what's going on. So you can see the network graph.png.
Talking about our methodology we use, firstly we use a different topology than the paper did in the simulated environment. On the right is a picture of this topology. And we also used a RUU control, which is Python based, and built our code base from scratch. And namely, the RUU custom functions and implementation of RENET were the most difficult parts, but we also did bandwidth fluctuations in Mininet. Firstly, how our contributions is, how did we do bandwidth fluctuations? We used the Mininet TC link layer. We also tested this bandwidth fluctuations on a larger network than the paper. Finally, the controller, when it runs RENET, it only updates these routing tables in 3 cases. It's either the start or termination of a flow, and then a fluctuation in the bandwidth. And namely, these flows that we update, or the routing tables for these flows, is always a strict subset of the total flows to be efficient.
Okay, so let's take a look at some of the other logic in our controller code. The first is send stats request, which is called as the periodic update from the switch to the controller. So we can see that we call 2 algorithms, the flow stats request and the port stats request, which we'll show in just a second. And if we go a little farther down, we can see that we have in the if rerun, we have 2 ifs for when the flow is active and the rerouting countdown goes to 0. This means that the flow has just been inactive. And so because of that, we have to run the path selection, which is the RENET algorithm, because this is one of the criteria for when we run RENET. And we also install the path flows a little farther down, and as well as the flow store, and we calculate the flows per link. And these data structures are held within the controller because control information. The next function is the flow stats reply handler. And so we have to update the flow info with all of these variables. So we have the source destination pair, the current rate and the desired rate, and then some information about the active versus inactivity of the flow. And we also store the path and update the flow store. And then the port stats reply handler is similar, but for the link store. So we get the data path and the data path IDs. We update the new link info with these variables, and we also compare it the current bandwidth to the previous bandwidth. And if it has changed, then we know that there was a bandwidth fluctuation, and so we can see it again. We have a call to RENET here because this is another one of the criterias for which RENET is triggered. And then we update the flow store, flows per link. And we also have the install path flows, which is how the switch tables are updated to tell the packets where to go. And then the last place where RENET is called is in the packet in handler, and this is representing the start of a flow when traffic is sent. And we can see a little farther down that we have one last call to the RENET, and this is the third criteria for when RENET is called.
How do we measure the performance of RENET?
One way to do that is with bandwidth satisfaction, which is what the paper does. And this is the measured bandwidth divided by the desired rate, which, as we stated before, was set to be a constant. And to visualize this, we use a bandwidth satisfaction graph, which has the satisfaction rates on the x-axis and the number of flows achieving at least that bandwidth satisfaction rate on the y-axis. And one of the things the paper looks at is how this varies with different values of k, which is a parameter for RENET, which determines the number of shortest paths that are considered to select from. So here we can see the results from the paper. And again, we have no bandwidth fluctuations here. On the left is the satisfaction rate graph. And we can see that a higher line would be better performance because there are more flows that have higher bandwidth satisfaction rates, which means they're closer to their desired rate. We can also see that as k increases, as we consider more paths, the bandwidth satisfaction rate improves because we're considering more paths, which makes sense. Also on the right, we have a pretty clear trend that as k increases, the runtime also increases. And this will be important for the next graph. So here we have our results, which again, we do no bandwidth fluctuations to try to replicate the results from the paper. And we can see a similar trend. The bandwidth satisfaction rates are slightly lower than in the original paper, and this is because our topology is slightly smaller, so it is more likely for flows to overlap. Additionally, because the topology is small, the runtime increase by changing the value of k is not compensated for by finding better paths because there are less paths to consider in our topology. And this is also why we didn't include k equals 100 because it didn't make sense. And this is also why we can see that when k increases, the bandwidth satisfaction actually drops pretty significantly. And here is our result with bandwidth fluctuations, and we can see very similar trend across the board. Additionally, our bandwidth satisfaction does decrease slightly because we do have to compensate for these fluctuations with RENET. However, it doesn't decrease by that much, which is indicative of the fact that RENET is pretty good at handling these. And then we decided to look at the percentage of flows versus the bandwidth satisfaction rates when we change the number of flows that we study. The reason we decided to do this is because the paper only does 200 flows, and we can see a very clear trend that as the number of flows increases, the bandwidth satisfaction rate decreases, and this is because there's more overlap between flows. So let's take a look at how we actually run our code and get our raw output. So first we use EC2 and Docker to virtually run our code like the labs. So we do Docker compose build and Docker compose up. And then we run the Ryu controller. And this will just kind of initialize some of the things. And then we can run our Mininet script, which is going to add in the hosts and the switches and the links. And then finally, we can actually run the script, which is going to do all the traffic generation and give us our output. So these are going to be doing the bandwidth fluctuations and running RENET correspondingly, like we talked about. And then finally, it'll be outputting all of those satisfaction rates to a CSV file that we can use to visualize. And we can also change the k value every time we run the experiment, which allows us to get this data in terms of k that we obtained. Okay, so here we can see the output from our CSV file. So we have the start time, so each row is a flow, and we have the start and end time for the flow, and as well as the IP and the port number, and then the bytes received. And this information is used to calculate the bandwidth, and when we divide by the desired rate, we can get our bandwidth satisfaction rate. And so we use some pretty simple Python scripts to take these CSV files and convert them to the corresponding plots with matplotlib. So in conclusion, we can see that RENET is a pretty promising routing algorithm for situations in which bandwidth fluctuations are common or unpredictable, and particularly in the real-world environments, which is what the paper studies. But we corroborate the results from the paper in the virtual setting, and we provide additional evidence of its effectiveness. And one future direction would be to compare RENET with other routing algorithms such as RFWD, DICES, and Picard, which the paper only does in the real-world setting. And so that's all we have, and thanks for listening.